All right. All right. So, doing the 20th of March, 2026, daily problem. Absolute difference in a sliding submatrix. You are given m by n integer matrix grid and an integer k. For every contiguous k by k submatrix of grid, compute the minimum absolute difference between any two distinct values within that submatrix. Okay, return a 2D array answer of size m minus k plus 1 by n minus k plus 1, where answer ij is the absolute difference in the submatrix whose top left corner is ij in grid. It's the minimum absolute difference. If all elements in the submatrix have the same value, the answer will be 0. What? If elements... Oh, right, yeah, sure. Okay, a submatrix x1, y1, x2, y2 is a matrix that is formed by choosing the cells x, y. Sure, yeah, so like this is like your top left, and I assume this is your bottom right, x, all the cells x, y. So this is your smaller row, this is your bigger row, this is your smallest column, this is your bigger column. Sure, yeah, so top left and bottom right. So, okay, I think I mostly understand. There's one bit I was a bit confused about. Return, so I kind of understand why did you get this. Answer of ij, okay, let's just go through an example. So you have a grid 1, 8, 3, minus 2. Oh, sorry. Let's open that. There we go, okay. So this is, what is this? 3, 5, so POTD. 3, 5, 6, 7. All right. So for an example, if we have 1, 8, and then 3 minus 2, and k is equal to 2, then I'm assuming you have to take all the 2 by 2 matrices for every, yeah, so there's only one of them. And you're looking for the smallest absolute difference the minimum absolute difference in the submatrix whose top left corner is ij. So in this case, the top left corner is 0, 0. So top left corner is 0, 0. What is the smallest absolute difference? Well, you can wait. Is smallest absolute difference like, as in like, so you do 1 minus 2 is 3, and then so the absolute value is 3. Or if you did like 2 minus 1 would be minus 3, but then the absolute value is 3. So doing like a pairwise thing, we recognize that like the difference between these guys is 7, difference between these guys is 2, difference between these guys is 5, difference between these two guys is 10. So 2 is the smallest so far. This is 3 and this is 5. So I think the smallest you could get is probably 2. So my understanding is you should get like a, yeah, okay. So this particular submatrix with, you know, top left corner of 0, 0 should sort of give me 2 as my answer. And that's the only, so each inner array represents each sort of computed submatrix, and then we take a list of all of them. So that's fair enough. These examples are, oh, this last one's a bit bigger. Okay, so this is interesting. So for the 3 minus 1 example, you've got a matrix that looks like this, and your k is equal to 1. Well, you have two kind of options, right? So you can, so the first submatrix you have to look at is this one. That's the first contiguous sort of 1 by 1. In which case, I guess what they're saying is, what is the absolute? I guess they're defining if you only have one element. If it's a 1 by 1, then just return 0. So that's like the first thing, and then same kind of idea when you sort of slide across and look at this 1 by 1. And this would also get you sort of 0. So then this is your answer. Just to clarify, you're meant to make a 2D array, right? Okay, yeah, I mean, I knew that. I don't know why I checked that. But it's more about like trying to make sure I map the correct submatrix to the correct kind of output, like to the correct inner array in my answer. I want to make sure I do that correctly. Final example said 1, minus 2, and 3. 1, minus 2, and 3 for the first row, and 2, 3, 5, 2, 3, 5 for the second row, and k was equal to 2. Yeah. So now we have a couple, so we have a, not a 1 by 1, and we have a few submatrices to check. So the first one would be this one. Right, and we ask, okay, given all these elements, which is the one with the smallest absolute difference? So the absolute difference between these two guys is 3, the absolute difference between these two guys is 1, the absolute difference between these two guys is 5, 1 here, absolute difference between these two guys is 2, and here it's 4. So we got 1 as our smallest, so this guy maps to 1. What I'm assuming, wait, can I check something? Was it 2? This would have been 0, 0, not 2 separate zeros, yeah, because you slid across, not down. So 0 and then 0 as the first row, like, and then this wraps. So then as we slide across, we're still in the same sort of row in terms of our sliding submatrixes. Sort of, we've only gone to the left. And so what's the absolute difference here? Well, you got 5 here, you've got 2 here, 2 here, 5 here, 0 here, and 7 here, so 0. So it'll be like that. Oh, got that wrong. Was it minus 3 or something? Wait, what? Starting at 0, 1, you have minus 2, 3, 3, and 5. The distinct value... Oh, between the... Did it say distinct? Ah, sorry. I forgot about that. So just, you can only look at distinct values. So if there's only one... Okay, so I'll just write that down. If only one distinct value exists in a k by k matrix, then what do I have to do? I have to return 1 as my return 0 as my answer. But there's more than one distinct value here, so we just ignore this guy. So the smallest we can get was 5, 5, 2, 2, and this one was 7, so we ignore that other diagonal. So the smallest we can get is 2, and that's why you get that answer. Okay, fair enough. Okay, I kind of understand. I'm trying to think. So naturally the way I'm doing it right now is like, I'm, so to speak, I'm checking every pair within the k by k. Within the k by k, there's k squared elements, and I'm choosing 2, right? And I'm checking the absolute difference. So the amount of time it takes to choose the absolute difference for one of these subarrays is going to take that much time. And then from there, I have to sort of check, roughly m by n submatrices. So this is kind of my current time complexity. K, I'm assuming, can get quite big. Oh, okay, it's everything's relatively small, but still having a combinatorics thing was going to make, k squared, and there's going to be like a factorial, and then k squared minus 2, like, this is not going to be very good. Like having k squared, which could be 30, and then multiplying it by itself, and then multiplying another 30, and multiplying another 30. I think multiplying one more 30, because you got k squared minus 1 on the top, and then that will cancel with the rest of the k squared minus 2 factorial on the bottom, which just be 2. So Maybe you get away with it like this. We could code this up first, a complete brute force solution, but I do think there's ways of basically, because of the overlaps, like for any particular k by k sort of window that you're looking at, when you shift by one across, you're kind of losing k elements and you're gaining k elements, you know? A lot of the elements that you are getting between the two windows is actually very similar, you know? So I'm just curious if there's a way to sort of keep track of maybe what the absolute the thing is, like, getting an absolute minimum difference is always going to be about like finding two similar numbers, right? Like two numbers that are close to each other. So the actual values that these numbers have isn't going to be super important. It's more so how close these values are to each other. So I don't know if I can do this efficiently. The actual size of everything is relatively small, so maybe they're trying to support the brute force solution, but all I can really think of is, you know how I said you have to. All I can really think of is, I said here that you have to take all k squared elements and choose two. While that would be true for the very first submatrix, I'm hoping that because when you shift across, you would have done most of the pairs anyway. You don't recompute it. That would be my way of trying to achieve efficiency. Is like, it's kind of the same idea. If you're shifting across, a lot of these pairs that you've already checked, you know. So what I would probably do is have like maybe like a separate k by k window. Let's say a 4 by 4. Every time I, find the absolute difference of each. Oh wait, no, this doesn't work. So I'm thinking like, let's say if I look at this third example again, I say, okay, look, what's the difference between you and the element here? You know, what's the element? What is 900 choose 2? Because it's k squared, right? So 900 choose 2 is a crazy number. Oh, it's not that bad actually. But then you got to do that like a lot of times. Like you might have to do that 30 times or something. And then we start to get a problem. 1, 2, 3, 4, 5, 6, 7. Yeah. So you really don't want to have to rely on checking every pair every time. Um, How do I? Damn. I'm not too sure about this one. Something about like, if I have this element and I check, I check all other k squared minus 1 elements with it, right? And then I have this guy over here. And I make sure that how do I keep track of what the absolute differences are for each pair? Like, I was thinking I could do something like, nah, I got nothing. Damn, really? A medium problem's gonna get me? I have a big window. I slap it onto the matrix. If I naively compute all the even if I naively compute all the pairs, I guess my first problem is figuring out how to organize that information in a way that is like structured well, right? And I think you'd have to check all the pairs in the very first case, like in the very first window, because what else are you going to do, right? Surely. Um, let's say you traverse through that list, you traverse through that window, and you get all the numbers individually, in like a big list, a k-squared size list. And then, you do your whole thing, you do a double for loop, you check. And so that's like k to the 4, because it's like, that's like normally doing a doing a pairwise thing is an O of n squared traversal, but remember there's k squared elements originally, so k to the 4, which I think should be fine. 30 to the 4 can't be that big, surely. Oh well, fair enough. So you do that like once. You basically don't want to surpass probably k to the 4, like quadratic quartic time. So anyway, you do that. You can get your minimum. You can get your minimum there. That's fine. Then, when you shift down, okay, I have an idea. When you shift down, you lose like the first. How do I say the first? The first like k elements. I need to draw this better. Hang on. So let's say you have something like this, right? And let's say, so that's like your big matrix, and then your small matrix looks a bit like this. This is the k by k matrix. So yeah, you get all the elements, you figure out your min time, it takes k to the 4 time. Then, let's say instead of shifting across, you shift down, right? That means that you, right, you have lost the first k elements. There's k elements that you've lost by doing this, and there's k elements that you've gained. So if you were to like move, you could have like a left pointer that moves to the k plus 1th element. It'll be index k, but the k plus 1th element, and then you append whatever the next k elements here. So there's, the last k elements got added on, deleted the first k elements from the start. You still have k squared elements in total after you've done all this. And of course we could do another k to the 4 operation, finding all the pairwise, but you've already done, well, but I wouldn't have kept track of it. I don't really want to have to redo all these pairwise checks again. I'd rather just check sort of within here, like check if there's any good pairwise things here, and then checking sort of like the new zone with the old zone, like checking if there's a minimum absolute difference there, because these are the only new numbers I introduced to the window. Yeah, what if I keep track of the element? Sorry, what if I keep track of the absolute difference, the minimum absolute difference for each element when looking ahead and looking for an element ahead of it, never behind, only ahead. That way the double for loop still kind of does its job. But yeah, so like, index 1, this is like all the raw values, but then when we find its minimum absolute difference thing, we find the value we can make, and we put it sort of in a separate array. And then here we do the same thing, but put it here and put it in here, and here we look ahead, find the minimum absolute difference and put it here, and so on. That way, when we lose the first k elements, because we slid the thing down, we still sort of have a good sense of all the minimum elements we have left, you know? And let's say the best minimum absolute difference between this element and this element in the first window, this guy would have stored that, and we would have found it here. This guy wouldn't have stored it because he's only looking ahead for the next best minimum difference. So when we lose this value and we lose this best difference, it's not like we're going to falsely think, it's not like this guy's holding on to it and we're going to falsely think that that minimum difference still exists. So I think that's a decent idea. Anyways, we keep going. Yeah, and then basically for each guy here, we just check the last k elements, see if we can improve upon the minimum difference that this guy was holding on to. Do that again, and then for the k guys, we do that a bit more specifically. We check very particularly. This will be a k squared. This will be a k squared thing, and this will be like a is it k cubed operation? Like checking you, and then checking you, and checking you, and checking you, checking you, checking you, checking you, checking you, checking you, checking you. Actually, no, okay. I was trying to think, like, if I know the difference between these two numbers, and I know the difference between this number and like all those numbers, maybe I can do like a cheap trick, but the absolute value I think screws it. If I, like, for example, if I knew that between k numbers and some value x, I knew that the best difference, just difference, was like 3. So let's say there's like 5 here and a 2 here, and all the other numbers were really, far from 5. If the next number, x, or like y, which is right next to x, I don't know. This is a bit weird. Okay, maybe this will work. I don't know. K cubed. So it takes k cubed operations. So it takes 1k to the 4, and then a bunch of k cubed operations to like handle sliding down. And then we can kind of do a similar thing with columns. After we slide this green guy down one, and we do this whole, lose k elements, gain k elements. Maybe the issue is, like, we can't really do the same thing sliding this way, because losing the k elements in a column isn't the first k elements in this list. It's like, every kth element in the list, which is a bit annoying. So you can't really delete cleanly like that. What you can do though is maybe have 2 views for it. Like, you could, when you're constructing this first green list, which was actually this one, we could have like a row view of it, going row by row, and then we can have a column view. So where, like, a number is adjacent to another because it's right beneath it, or it's sort of starting a new column and going down. So like the first k elements, second k elements, third k elements, fourth k elements, like that, up to the kth element. Anyway, so because of, like, if I have 2 views, then it's a similar idea if I slide this one across. But my issue is, if I slide it down, I have the row-wise view of this element. Do I really want to construct a column-wise view? I guess I could. I could just, if I Oh wait, I don't need both views for this guy. I only need the one that's required to go. Hmm. I have ideas, but they're very strange. if I'm lucky, it's k to the 4. Or maybe like it's k to the 4 plus like m n k to the 3 or something, which is like 30 to the power of 5, which is 24 million, which I maybe get away with. Maybe 10 to like maybe I don't actually. I feel like 10 to the 6 is kind of as good as you can get before it starts the TLE. Do I want to try coding this up? This is very bad, like, working. I think the idea kind of makes sense. It's just that it's not very good. All right, so just to summarize, right? Because I don't think I made any sense this whole time. I wonder how much time I've taken. Probably like 20 minutes. What is the time? 12. Okay. I'll do this one with like 10, 15 minutes and then I'll go. Basically, we're going to look at the first, so I'll like give myself a new like bit of space just to like freshen my mind. So you're given an m by n matrix, right? We're going to place a k by k matrix sort of over the top. And for this very first k by k, I think we're going to do two things. We're going to construct a row view, which is going to be a k squared array. So I'm going to call it row view. K squared array that takes the first k elements in the first row, right? That first row of k elements, it's going to write those ones first. So like row 1, column 1, row 1, column 2, up to row 1, column k. I'm one indexing, I don't know why. That's like the first k elements. And then row 2, column 1, row 2, column 2, etc. up to row 2, column k, and so on, right? So that's the first, this is like row 1, this is row 2, etc. That's going to be the view for k squared elements. We're going to do a very similar idea with columns. Call it the column view. Whoops, need a thicker pen. Column view, where we're going to look at the columns and write it in the column order. So it's going to be like another k squared array, and it's going to be like column 1, how do I write this? Row 1, column 1, row 2, column 1, row up to row k, column 1. So it's these elements first, column 1 and all the rows, then row 1, column 2, like we're looking over here now, row 1, column 2, up to row k, column 2, and so on. So we've got two views of the same matrix. Okay, that's fine. So to figure out like the minimum view, the minimum absolute difference, it's going to take a double for loop across, finding all the pairs and finding that minimum between all the pairs, right? In the meantime, we're going to produce two more arrays of size k squared. That's going to be like the best min difference looking ahead. Now this double for loop will do this for me, but basically each value in here will store the smallest absolute difference between, if this is index I and all index j, where j is strictly greater than I. Right, so I'm saying like, I sort of said this earlier, but like looking at this element, I'm allowed to try and produce my best absolute difference using all these elements. But if I look at this element over here, I'm only allowed to use the ones ahead to try and make the best absolute difference. And that's what this guy will store. And I think I'm going to do that twice. It might seem redundant because the final answer I get for this window will be the same because I'm looking at the same elements. But I'm going to do a row-wise version. I'm going to do a col-wise version. Both of these referring to the same kind of idea, but this is looking at it column by column, and this is looking at it, this one is looking at it, sorry, I think I said it wrong. This one's looking at it row by row, and this one's looking at it column by column. But yeah, and then whatever the minimum, like take the minimum of all these values, will get me the first the first value in the answer, basically, because it's the smallest absolute difference in the whole window. Now, that seemed like a lot, and yet that's only one window. So if I want to, now this is where it gets weird. If I want to shift it across, let's say down first. If I want to shift it down, meaning I lost the first k elements in the row view, and I gained the next k elements in the col view, then I will basically, so shifting down, as we have in the green, I probably won't delete these elements. Actually, it probably won't matter. Honestly, it might actually just be easier, because considering what the time complexities are, and an O of k operation of like deleting, oh, is it O of k? No, because I have to shift it down by k elements as well. So it's more like, it's k elements, but then also k shifts. Oh, but is that still okay? Wait, I'm tripping out. If I delete this element, then I have to shift it down by 1. Delete another element, shift it down by 2. So it's k squared shifts. K plus k minus 1 shifts plus k minus 2 shifts, etc. There's k of them. Okay. So that's in k squared. Again, it still might be worth it, honestly. Because the other option, my original option was basically move a pointer down to point over here to be like, look, ignore all these elements, you know? Which is not difficult, but this array will get very big. But maybe it doesn't matter. Is it better to just remove it, bite the bullet, take a k squared operation? I mean, to be fair, I'm going to be doing k squared operations anyway. If I double that number, it probably won't matter. So let's say we pop first k elements from row view, and we append elements from I suppose the k plus 1th row. So like, you know, this is the kth row that and now we're shifting down to the k plus 1th row. Again, I'm one indexing, I don't know why. We append all these elements sort of found in there. And then we can basically shift that, and we can basically apply the same idea where this is the row view, right? We can basically say, look, take this array, right? Because that was what was produced by using this row view. I think we can, yeah, do a similar idea, to pop the first k elements, and then maybe append k infinities on the end, and then we do kind of a similar double for loop, except we don't care about looking at these elements. Oh man, how do I write this out? So the row view, which originally had, you know, R1 and stuff, it will only have R2 now, R2, C1, R2, C2, etc. And it will end with RK plus 1, yeah, C1, etc., right? Like it will be the row K plus 1. We've already done the pairwise checks, and these arrays store the best min distance for these checks, right, across these checks. So now all I have to do is look at the last k elements in this array and see if I can make any improvements. So for what would it be, for I in range, sort of from 0 up to the end, or I guess 1 because I was 1 in checking, but whatever. And then basically for j in range, basically I'm just looking at the last k element, so like -1 to -k inclusive will probably work anyway, I think. If the absolute difference between, you know, this guy, x at I minus x at j is, you know, if it's smaller than the current sort of the memory at I, then update, sorry, the absolute value should be here, then update the memory of I to be x of I minus x of j, absolute value kind of thing. I don't know if this makes any sense, and this is only shifting down, and then when I shift across, until it, you know, stops fitting. I shift across until it stops fitting, and then I shift down. And then for all of these things where I shift across, I shift down a bunch. So like that's like the third one, and eventually I get to the end, and then for each of these windows, I just shift down a bunch, and I should have all the windows I need. Oh, man. This can't be right, by the way. Like, this is way too convoluted to be correct. I already know, but I just don't know what else you meant. Like, that's the only real... I've reduced a little bit of redundancy. I don't know what more to really do. I don't even know if I made any sense this whole time. I don't think I did. Shifting across, you do a similar thing. You pop the first k elements from col view. You also do the same with the corresponding red array. Pop the first k elements. Append the next k elements from the k plus 1th column, or the next column across, and then also append infinity a bunch, k times in this red array. And then, yeah, compare the last k elements, find the minimum difference with all the other elements, including within themselves, and update this array to reflect the best thingy. So let's say that makes perfect sense and that nothing bad happens. Then I don't need to, like, for every only the very top row of submatrix needs to have 2 arrays. Everything else, once you start moving down, you can just keep moving down. You don't have to move across anymore, because once you have all these windows that you've placed, if they all move down, right, independently of each other, they will all find the corresponding answers for their, like, columns. You know? Probably that didn't make any sense, but like basically my point is only the first row needs to keep track of the row view and the column view. After that, after you have the row view and column view and you shift across, then you take the first guy, shift him down, take the second guy, shift him down, take the third guy, shift him down, take the fourth guy, shift him down. Or maybe it's better to go in this order. Take the first guy, shift him down completely, but keep track of his row view while you do that. So this is the row view of the original guy, but just keep shifting him down, editing the col view as you go. Then, using the row view, shift him across. No, but I need his col... Wait. I need the... Wait, what? Bro. So let me try thinking about that again. So you have the first view, you have a row view and a column view, right? Going row by row and going column by column. This is getting so messy, but when I shift across, I have to delete this, gain k more thingies. And then, yeah. Put the next k. Wait, this is row view, so this is when you shift down. If you shift down, you have to lose this, put k more on the end. The issue is now the column view still refers to this old guy. And so you could use him to shift across. Just trying to keep in mind time complexity. Like if reconstructing one of these arrays is k squared time, or is it k to the, no, yeah, k squared time. Reconstructing this array is k squared time, and this one is k squared time. And then constructing these corresponding arrays is also, I think, k squared time. And then it takes, so it's 4k squared, and then a k to the 4 operation to do the pairwise, the double for loop thing. That's sort of the very first, array. And then for the next array, let's say we, we take this guy, shift him down, so the row view chops. That's an k squared, I think, operation if I'm doing popping, and then another k to append to the back. Do I want to be able to... Okay, here's my dilemma, right? I don't know if I've made it clear. When you move across to get, this guy over here. Okay, I should probably clean something up. It's a bit better. Okay. Originally, the submatrix starts at this k by k position, right? When you shift across, like this, the column view should change, right? Because you lost this first column, you're gaining this new column. So you chop off the first k, you add on the new k. Fine. But now the row view is messed up. Because, like, this is not correct anymore, right? Like, you should be chopping off these elements from here, every kth element or whatever, and then applying it, sort of inserting them. Like, it's a weird operation to try to fix it straight away, right? So I thought I could ignore it. I was like, I won't fix it. I'll just make sure the column view is correct and the row view will just be wrong, which I thought would be fine. And for the moment, you would be able to calculate the min absolute difference using just the column view. That's fine. But then, if my plan was to shift this guy down in order to get, because my plan was to shift this blue guy down so I could get this window as well, but the row view is messed up. So then I would have to reconstruct the row view for this blue. Oh, I should get the blue pen. I would have to reconstruct the row view for this particular blue matrix, k by k matrix. But then, let's say I just do that k squared time, that's fine. Let's say if I'm willing to do that. But then I just feel like this will be messed up. Because... like, I feel like I'd have to recalculate this entire thing, which would be another k4 time thing, because this was keeping track of the red pairwise best differences. When I move across and lose the column, then it makes sense to chop off, the first k elements from down here, but it doesn't make sense to... I think I've missed something. I think there's something major that I have to figure out, and I don't think I'm going to right now. There must be some kind of efficiency thing that I can add, because there's no way this is going to work, I think. Like, trying to keep track of... It was a nice idea at first, but it just doesn't really hold when you're trying to move around so much. Like, all these updates are going to be too expensive. Um... Hmm. I'll give myself till, yeah. If I gotta cheat, I'll cheat tomorrow. Like, I'll wait till the streak gets killed before I cheat. So, yeah, I don't know. I can't tell because I feel like the general idea makes sense. Like, all the pairwise differences for the overlapping section. So just check the new introduced elements. But I can't know if I've overcomplicated it by adding like so many lists. They felt necessary, but they don't even completely help actually. So, oh no, that doesn't work. Sorry, I thought of something, but it doesn't work. Um, this is kind of like a machine learning thing, right? Like a deep learning thing. Got a kernel, and you're like moving it across, and you're like figuring out the value that best somehow summarizes the data. Normally, it's you do like a max pooling thing, but like this could be a function as well. Minimum absolute difference. The difference is though, in those machine learning cases, normally you're looking at like one value. It's common, like a max pool, you're looking for the biggest number, which is a k-squared thing. Here, you're like the output relies on two numbers. So naively, you have to compare all the pairs. But when you shift across, you shouldn't have to compare all the pairs, right? Like you should be able to just deal with the pairs that are new. 1, 2, 3, 1, 2, 3, 2, 3, 1, 2, 3, and then between them as well. There's got to be something, man. M. Are there hints? I'll take a hint. Use brute. You serious? No, that can't be right. Like brute force, brute force? No, that can't be. Sorting. Is it legal to sort? Use brute force over the submatrices. Really? So you got like, but the thing is like, they recognize that there's k to the 4 pairs, roughly. And then you gotta do that like, alright, I mean, look, we can try it. Maybe they've construed the test cases so that there'll never be too much computation, but surely brute force is a bit crazy. Like, no, there's no sense of like using the previous result to inform the next result at all. Like, all right, so well, okay, if we're going to brute force absolutely everything, then left is equal to 0, right? That is to say left column. Right column is equal to k minus 1. AKA, really, you could just say it's equal to, I think, left col plus k minus 1. Like, that's the general formula. You wouldn't really need a separate variable, but it's fine. I'm just going to... Top row is equal to 0. Bottom row is equal to same kind of thing, k minus 1, but you could also just always infer the bottom row if you wanted, but it's nice to have separate variables. While, I guess, the right column, I should get the dimensions actually. So the num rows is equal to the length of grid, the num cols is equal to the length of grid at 0. While the right column is sort of a valid thing, like a valid index, is less than the number of columns and okay, we'll do it like this. While the way I'm thinking about it is like I'll shift across and then I'll shift down and go across again. You know, like I'll do this guy first and then I'll shift across a little bit and then I'll go across a little bit and across a little bit, which means I have to check the outer, I have to check the bottom row first. Well, bottom row is a valid index, so while it's less than num rows, and then it'll be double nested. Answer is equal to this one. Current row answer is equal to this one. Min diff is equal to omega helper. Get min diff given the 4 left col, right col, top row, bottom row, and the grid. I might not need to give k explicitly because I've already been very specific about where the borders are of the matrix. Def, what do I call it? Get min difference. So self, and when I say grid and then left, right, top, and bottom. Okay. So, how do I want to do this? Maybe I will just give k as well, just to make my life easy, rather than doing extra computation. The number of elements is equal to k squared, right? For I in range, num elements, for j in range, I up to the number of elements. This is just giving me a unique ID for each element. Min diff is equal to float of infinity. Min diff is equal to the minimum between min diff and the absolute difference between grid at, not ij, this is the issue, because ij is going to be 0, 1, 2, like that, but depending on where your L is, okay, let me think about it this way. So I refers to the current element you're in, that is the boss, you know? I refers to the current element you are on the left-hand side. And so, to figure out what row and column, you need to think about the fact that like if I is 0, that means you're at row R. You're at the, sorry, maybe I should say right call, left call, top row, bottom row. So if you're at 0, that means that you're at 0, 0 relative to, you know, these, the left call and the top row. Maybe that's how I can do it. So bearing in mind that your at row is, how do you do this again? Is it I mod k, or I divided by k maybe? That tells you how many rows you have passed, and then at col is equal to I mod k, and then I think you have to like add the top row or something. You have to add the left column. It's like my understanding. And then j at row will be j, this will be this thing, and then j at col will be j mod k plus the left col. I don't know if this makes any sense. Let me, okay, all this can go because I'm brute forcing now. So let's say, right, we have this matrix, and then within that matrix we have like something like this. It's a 3 by 3, and then starting at, you know, left column is 1, top row is 1, right? So this would be, I'm labeling it 0, 1, 2, 3, 4, 5, 6, 7, 8, right? That's what this is. Like, number of elements is this for I in range 0 up to 8, basically. The row I should be getting, so with, if I'm at, let's say, 4, right? If I is equal to 4, that means, well, given that k is equal to 3, I know that I'm in the first row because 4 divided by 3 with the floor is equal to 1. That means I have passed through 3 elements, no problem, one set of 3, and I'm sort of here now. But because because this red is not anchored at the start of the blue, I have to add another one because, you know, we have to shift the red has been shifted down by a total of 1. So if relative to the red, the 4 is in row 1, then relative to the blue, the 4 is in row 2. So I have to, yeah, so I think this will make sense. I think this is right. You do the floor thing, and then you add the top row. And then by similar merit, when you do mod, you're basically saying, so for mod by 3, that is this ID modded by the k gives you 1, telling you that you are in the first column, in index 1 column relative to the red, but the red was shifted by 1 from the blue, so you have to add another one to get 2. So 0, 1, 2. Yeah, so I think this is right. And then basically, I at the row, I at the col, minus j. And then you return min diff. You're happy with that, and then you basically be like current row answer dot append the min diff, and then answer dot append the current row answer, and then return answer. So yeah, look, maybe if this works, then fair enough. But I don't know. It just feels super redundant. Like going through. Maybe when they say brute force, they don't mean this brute force. You know. I do think this will TLE. Oh. Is it an indent problem? Really? Is this like too far? Does not match the unindent does not match. Is this fine now? I'm confused. I don't know what just happened. Huh? I'm tripping out. What's going on? Oh, whoa. Why did that happen? Oh, I did not realize that had happened. I didn't even clock that. Oh, wow. Oh, there you go. Oh, I didn't move. My bad. So you do this, and then the right col should equal 1. I didn't actually shift the... So the left and right column should shift by 1. Then this will exceed, and then the left col should go back to 0. Right col should equal k minus 1. And then to shift down, the top row should increase by 1, and the bottom row should also increase by 1. Do this first, and then do that. So I guess technically I don't actually have to define the column stuff here. Well, I didn't account. I didn't really account for the fact that I forgot to account for the fact that you could have the same number twice. So if this one came with a 0, that makes sense because it saw the 3, 3 and thought that was smallest. But I don't understand why everything's a 0. Everything is 0. That's fantastic. Did I return? I did. Did I changed this, right? Grid at... Oh, man. This is going to be a pain to debug. This should be I plus 1a. Whoops. Okay, what I need to do is have a thing where it's like... Do I have to traverse twice just to check if there's... Okay, hang on. This is what I'll do. If this number is the same as this number, then just continue. Else, I don't need an else. Otherwise, do the update. Now, if we go through this entire thing and mindiff is still equal to float infinity, that indicates that every time we tried the pairwise thing, it never changed. Like, every time we tried the pairwise check, it always continued, which means all the elements were the same, and therefore we had problems. Okay, well, if this works, I feel scammed, I would just say, because I feel like the difficulty of this problem was meant to come from trying to reduce redundancy, but I have just... Nah, this is gonna TLE, there's no way. This is like m by k, basically. I guess if k is big... Sorry, not m by k, I was going to say m by n. I guess if k is big enough, then there's not actually that as many submatrices because, like, you know, I guess the bigger k is, the less submatrices you have. The smaller k is, the less checks you have to do within k. So maybe that's what it is. Overall, though, like, I feel like you're checking... I don't know. I mean, they even tell you how many Like they tell you that there's mn minus k squared minus mk minus, like this is how many elements you're doing. This is how many windows there are. And for each window, you've got k squared, k to the 4. That's the thing. So in my mind, time complexity looks like this. You got that. So this is how many windows there are. M minus k plus 1, n minus k plus 1. And then for each thing, you're doing a k to the 4 operation. Because you've got a k squared window and you're doing like pairwise across all the things. So that's k to the 4 checks, basically. Obviously, it's not quite k to the 4. You got the whole arithmetic sequence thing, 1 plus 2 plus whatever. But like, so you get like mn k to the 4. Granted, minus, you got like minus a k to the 6 in there, which maybe is quite, and considering k is as big as mn, I guess you basically can say m, like if everything is just m, you got m to the 6 minus what? M to the 6? What are the other positive? But then you've got plus, it feels like k to the 6, like you got a k to the 6 in there. Plus k, I just don't, anyway, screw it. This feels, all right. All right. Well, at least the streak continues. But I want to see what this is. What is the? Oh, of course. Oh, so there is sorting. I never would have thought of that. All right. Let's see. So you get the row, you get the columns. Fine. You get the res. I assume that's the final thing you return. For I in range n minus k plus 1. So that's telling you this one. So that's the number of columns. So this is like all the shifting across you got to do. Res dot append. So you got like a new submatrix, I assume. For j in range m minus k plus 1, you use a set, fine. So for j in range m minus k plus 1, that's this one. So that's telling you how many rows there are in your answer. So it's like you're shifting down, basically. So you get a set. Min difference is 0. Interesting. For r in range... Wait, what? For r in range 1 up to... Okay, yeah, you're like going through that. For this one and this, you get a set. You sort it. Oh, of course. It's the adjacent numbers will have the smallest difference. I forgot. I knew that. I should have known that. That's what the sorting is for. Then you don't have to do k to the 4 operation. That's what it is. Oh, it's so silly. I should have realized that. Especially when I cheated, checked the hints or whatever, and checked the topics, and it said sort. It didn't even occur to me. Minimum absolute difference. You look at the gaps between adjacent numbers. Like if two numbers are here and here, and they're like this, then there's no, and you got another number here, and you check this. There's no point checking this. One of these two gaps will be smaller than the. Oh, that's really silly of me. Oh, I'm actually kind of embarrassed. I can't believe I didn't think of that. Oh, wow. And that's filmed. You saw what goes through my mind when I do this kind of problem. All right, let me do this properly. Hang on. I'm gonna fix. I have to at least do it right. It's one thing to read it, but I can't believe that. So the nums are this. I guess. I think I prefer doing it this way, because it's like, because what he did was have a set, and then add to the set, and like use the set as a way of like Well, it is quite clever actually, because by having only one element, if you only have one element, there's no gaps to check, so you return 0. That's quite, yeah, that's fair enough. But I was curious if min 0, oh, okay, yeah, so you do it if it's equal to 0, then do the update. Okay, fair enough. Um, God. Okay, so like all nums is equal to this one, and then yeah, instead of doing it like this, all you want to do is so you don't need that anymore. Maybe I do want to set actually. Yeah, it should be fine. I all nums dot append grid I at row I at col. And then we do all that, and then all nums dot sort, and then for I in range 1 up to the length of all nums, if all nums at I is equal to all nums at I minus 1, then just continue. So this is the same kind of idea. Otherwise, min diff is equal to the minimum between min diff and the absolute the absolute value between all nums at I. Well, actually it's sorted, so I don't even have to do absolute anymore, because I is definitely be bigger than, not that it really means anything, but you know. And then yeah, if min diff wasn't touched, that means that all the time we had the same value, so we can just return 0, otherwise return min diff. And this was infinity originally. God, sorting. Okay, yeah. Makes sense. Oh. What have I done? Not enough brackets? Too many brackets? Oh yeah, because I had the abs. So I had an extra bracket and I only deleted half of it. Fair enough. Yeah. I am curious. So how did that person? Because I don't think he did like the modulus thing. So he just, yeah, he went from like from R in range. Yeah, fair enough. Like he used the size given, which is smart than what I did. Anyway, that's fine. Oh, I really don't want to put this one on YouTube. But I will. It's important to remember your low points.